What you see here isn't magic. It's simply air being used to transmit energy. Air is in plentiful supply everywhere. When air is compressed, it can be used to perform work. This is known as pneumatics. Here, air pushes on a device, moving it back and forth. It's controlled by a simple pneumatic control system. Pressing the button sends air to the cylinder. The control valve in the center of this circuit determines which side of the cylinder receives the air. The push-button valve at the bottom of the circuit sends signals to the control valve. Therefore, compressed air acts as both a working and control medium. Pneumatics, or using compressed air to transmit energy and control functions in systems, has several advantages. Let's examine examples of each. Compressed air is fast. For example, short cycle times can be achieved in automated assembly applications. At the same time, it is overload safe. If the machine jams, pneumatic motors or circuit components will not burn out. Another advantage is that compressed air is clean. This is very important in the textile and food industries, where sanitary conditions are of primary importance. Pneumatics is also safe because compressed air does not burn or explode under a wide range of operating temperatures. In addition, the exhaust air can be discharged directly into the atmosphere. Pneumatic systems are heavily utilized in cleanroom applications for the same reasons of cleanliness, low combustion, and fast operating speeds. Compressed air can also be stored, ready to be used when required. Another advantage is that compressed air does not break down when exposed to high temperatures, thereby allowing for safe, consistent operation under a wide range of temperatures. And finally, the individual pneumatic components are inexpensive when compared to other forms of energy transmission and control. Pneumatic control and actuation is an ideal energy for automation of industrial processes. A knowledge of a few basic principles of physics enables you to gain a better understanding of pneumatic systems and how they function. Let's start by defining pressure. Atmospheric pressure is present everywhere on Earth. It's generally regarded as being a constant at sea level of 100 kilopascal, abbreviated kPa. All pressure measurements taken using atmospheric pressure as the 0 point are designated gauge pressure, or P sub G. Pressure gauges attached to pneumatic circuits usually indicate pressure as gauge pressure. From this point on, whenever P is used without a subscript, it is indicated in gauge pressure. Absolute zero pressure is 100 kilopascal below gauge pressure. Any pressure below gauge pressure is called vacuum, or P sub V. Therefore, absolute pressure is the sum of vacuum and gauge pressure. Like all gases, air has no particular shape. It assumes the shape of the container. When air is compressed, it's storing energy. When the compressed air is released from the container, it can be used to perform work such as moving an object. In summary, the mechanical energy of the piston pump moving in and out can be converted to compressed air. The energy can be stored in a container, in this case, the balloon. As needed, the energy can be converted back to mechanical energy, as demonstrated by the toy truck. Another example of the conversion of energy. In this case, the air pressure generated is applied directly to the cylinder. The force generated by the compressed air is then converted by the cylinder back to mechanical energy, lifting the load. Next, let's study the relationship between volume and pressure. The volume of this cylinder is 2 liters, and the pressure, as indicated on the gauge, is 100 kilopascal. This relationship can be described by the formula V times P equals a constant value. To test this, let's enter the two values into the formula. Multiplying these two numbers results in an answer of 200. When you press down on the piston, reducing the volume in the cylinder to half its size, the pressure gauge now reads 200 kilopascal. Applying these new values to the formula results in an answer of 200. Pressing down on the cylinder until the volume is cut in half again results in a volume of 1/2 a liter and 400 kilopascal. The new numbers again equal a constant value of 200. This example demonstrates the relationship between pressure and volume. For all of the volumes, the product of the two values remained constant. Next, let's examine an application of this concept. If you have a compressor with an output of 7:1, you can use this formula to determine its output pressure. The known values are the starting volume V1 of 7 liters, the end volume V2 of 1 liter, and atmospheric pressure P1. To determine the output pressure P2, use the formula V1 times P1 equals V2 times P2. Enter the values and solve for P2. When you're finished, P2 should equal 700 kilopascal output pressure. When you subtract the starting pressure, the compressor increased the pressure by 600 kilopascal. The compressed air used in pneumatic circuits must be clean and dry. Let's examine the devices used to produce compressed air. Compressed air can be produced using stationary or mobile compressors. Both types use various designs to compress the air into a smaller volume. Two of the most common types are piston and screw compressors. The drawing on the left represents a reciprocating piston compressor. When the piston moves down, it draws air into the cylinder. It then moves up, compressing the air. Compressors that contain one cylinder are called single-stage compressors. Each stroke of the piston produces a burst of compressed air. The screw-type compressor consists of two threaded shafts that are intermeshed. As they turn, they transport air from the intake side to the compression side. One advantage of this type of compressor is that it produces a continuous flow of air. In both types, as the air is compressed, energy in the form of heat is concentrated in a smaller space. So, most compressors include a cooling unit to reduce the temperature of the compressed air. Such units can also be used to reduce moisture, oil, and dirt in the compressed air. The compressed and cooled air is then stored in a tank called a reservoir, which performs several functions. It acts as a buffer, smoothing pressure fluctuations as the air is used by the circuit. This also allows the compressor to run only when needed to pressurize the reservoir. The reservoir also supplies a steady flow of air to control circuits. This reduces fluctuations in pressure under varying rates of use. In addition, the reservoir helps to cool the compressed air. As the air cools, moisture separates from the air and collects in the bottom of the reservoir. This water must be drained from the reservoir on a regular basis. Not all of the moisture is removed in the reservoir, so in order to prevent corrosion of valves and other components, a dryer is often included in the system. When designing and installing a compressed air system, the distribution of the air has a major effect on system performance. The size and layout of the pipes is critical for economical operation of the system. The design should also allow for future increases in demand because modifications can become very expensive. Connections to the main piping should be done from above to prevent water from flowing into the machinery. The system should also include fixtures that allow water to be drained off. In addition to the preparation of compressed air during its production, a service unit is used to prepare the air when it enters the machine circuit. These cutaways show the intricate air passages typical of pneumatic components. It's important to remove dirt and moisture that may have been picked up by the compressed air from the distribution system. Dirt could clog component air passages, and water could cause corrosion of valves and fittings. This is a cutaway of a typical service unit. It has four main features. Let's identify each one. It contains a filter element, condensate bowl with drain, pressure regulator, and lubricator. In addition to removing particles carried by the air, such as rust, the filter also removes moisture. The moisture is collected in a bowl attached to the regulator that should be emptied on a regular basis, then removed and cleaned. The filter element should also be replaced when it becomes coated with dirt, such as rust particles. Air pressure in the distribution system is normally higher than that in the machine circuits. The pressure regulator on the service unit controls the pressure entering the machine. Some pneumatic systems use components that require lubrication. The lubricator in the service unit, when filled with oil, adds an oil mist to the compressed air. But oil should not be used in applications requiring sanitary conditions. These pneumatic cylinders are used to raise and lower manufacturing tools. This is an example of how pneumatic actuators convert energy in the form of compressed air to mechanical energy. To understand how they function, let's study a number of types of linear actuators. This is a transparent model of a cylinder. The linear cylinder is the most frequently used pneumatic actuator. Compressed air energy is converted inside the cylinder into linear motion. Cylinders are available in a wide range of shapes and sizes, normally within the following specification ranges: bore 6 to 320 millimeters, stroke 1 millimeter to 2 meters, force 2 to 50,000 newtons, piston speed 0.02 to 1 meter per second. Now, let's examine how cylinders function. This is a single-acting cylinder. It's represented by this ISO symbol, which indicates that the cylinder has one air inlet port and a return spring. When compressed air is supplied to the inlet port of the cylinder, it pushes against the piston. If the force generated by the pressure is greater than the force of the spring, the piston moves away from the inlet port, compressing the spring and extending the piston rod. When the pressure is released, the spring moves the piston back to its initial position, retracting the piston rod. The force of the spring, air pressure level, and piston area affect the work capacity of the cylinder. Single-acting cylinders perform work only in one direction, the extension of the cylinder. They are used in applications such as clamping or the ejection of workpieces. In applications requiring work in both directions, the double-acting cylinder is used. This is a double-acting cylinder and its ISO symbol. Note that it has two inlet ports and does not contain a return spring. In the double-acting cylinder, the force exerted by the compressed air can be directed against either side of the piston. This allows work to be done on both the extend and return strokes. Note that the area occupied by the piston rod also reduces the force generated on the return stroke. Due to the area occupied by the piston rod, less air is needed for the return stroke. When selecting a cylinder for a specific application, you must take various factors into account: stroke length, extension force, and retraction force. And finally, cycle speed. Next, let's examine the relationship between force and speed. In this example, with equal loads, both pistons extend at the same speed. If the load on the left is increased, the cylinder extends more slowly. If yet more weight is added to the load, it slows even further. So, with equal pressure and cylinder size, increasing the load decreases the actuation speed. If a load is applied which equals 75% of the cylinder's capacity, the extension speed will equal 1/2 the speed when there is no load. Next, let's examine the effect of changes in pressure. Here, a cylinder under load is extended using an operating pressure of 380 kilopascal. If the weight of the load is doubled, the cylinder will not extend until the pressure is increased to 600 kilopascal. This demonstrates that there is a direct relationship between operating pressure and load. Next, let's study the effect of changes in cylinder bore size. The bore size is the inside diameter of the cylinder. These two cylinders have different bore sizes. Using the same pressure and load, the cylinder on the right cannot lift the load. However, the cylinder on the left with the larger bore size is able to lift the load. Let's measure the difference in force. The small cylinder shown here has a diameter of 16 millimeters. It exerts a force of 106 newtons when operated at 600 kilopascal. A cylinder with a diameter of 25 millimeters, using the same pressure, exerts a force of 262 newtons. When the same pressure is applied to a 32 millimeter cylinder, a force of 418 newtons is produced. This relationship can be shown by the formula force F equals piston area A times the pressure P. The diameter of the piston directly affects the force, speed, and air consumption of the cylinder. The most efficient design uses the smallest cylinder adequate for the application. In this machine, various size pistons are used based on the job to be done. For example, the movement of materials requires a different force than clamping or the movement of heavy tools. There are some applications where the full speed is not desirable at the end of the cylinder travel. These applications require a cylinder with adjustable end position cushioning. This feature slows piston travel at the end of its stroke. End position cushioning is accomplished by restricting the flow of exhaust air during the end of the stroke. This results in the air being compressed in the cylinder and opposing the movement of the piston. Next, let's examine other types of cylinders. For example, this double-acting cylinder has a double-ended piston rod. This design provides more precise linear movement due to the two bearing surfaces. When heavy tools are not mounted along the axis of the cylinder, their weight applies forces to the side of the cylinder that can be compensated for by double-ended piston rods. Another advantage of double-ended piston rods is that the end not used for the application can be used for other functions, such as end position sensing. Another type of cylinder design has a hollow piston rod. This can be used to hold wires connected to a device at the end of the rod, such as an electromagnet. Or it can be used as a passage to carry vacuum or liquids such as oil. These cylinders have a fitting on the end of the rod for the connection of the tubing. This cylinder has no piston rod. Built into the piston is a ring-shaped permanent magnet. Mounted on the outside of the cylinder is a part called a yoke. It also contains a magnet. The piston and the yoke are magnetically coupled. As the piston moves, the yoke moves exactly the same distance. Rodless cylinders are ideal for long-stroke applications, effective up to 10 meters. Multi-positioning can also be achieved using cylinders, in this case with valves and multiple sensors. Another form of multi-positioning uses two double-acting cylinders joined together. If the cylinders are of different length, this design is capable of achieving 4 different positions. For example, the 4 positions are used in this machine to drill and countersink 2 holes. Cylinders convert pneumatic energy into mechanical energy. So far, you've seen how this produces linear motion. Here, the linear motion is converted into rotary motion through a gear train. As the piston rod moves, the rack on the end of the piston rod turns a gear, producing rotary motion. As the piston moves left and right, the gear rotates in the opposite direction. This machine uses a rotary cylinder to convert pneumatic energy into a powerful force for a stamping operation. Another design is the rotating vane cylinder. In it, compressed air directly produces the rotation. It functions in the same way as a double-acting cylinder in that it has fixed stops at both ends of the stroke and performs work in both directions. In this type of cylinder, the angle of rotation is adjustable. Rotary cylinders can be used in a number of applications. In this example, it's moving parts from a test station to a conveyor belt. Another use is for parts orientation. Here, a rotary vane cylinder is used to turn parts over for machining on the opposite side. Rotary motion can also be accomplished through other designs. One design, the rotating vane motor, is capable of producing continuous rotation. This pneumatic screwdriver can reach speeds between 3,000 and 8,000 RPM. The vane motor works by means of a rotor located off-center in a cylindrical chamber. Movable vanes located in rotor slots are forced outward against the chamber walls, sealing the individual chambers. Air enters the smallest chamber, turning the rotor as it expands with the increase in chamber size. The air is then exhausted when the chamber reaches its maximum size. Rotating vane cylinders are available in right, left, or switchable rotating versions. At this workstation, 2 vane motors are used to drive pneumatic screwdrivers for the assembly of electric motors. One advantage of pneumatic motors is that they can be used for applications in which a maximum torque should not be exceeded. This is the symbol for a rotary actuator with a limited angle of rotation. A different symbol is used to represent rotary actuators with unlimited rotation called pneumatic motors. These are a good example of how symbols reflect component function rather than structure. In pneumatics, valves serve a number of functions. They can be used to open and close flow paths, regulate pressure, adjust flow volume, and direct flow through various paths. One type of valve is the directional control valve. It has three basic functions. They are to block the flow path, to open the flow path, and to direct flow. Directional control valves perform all three of these functions when they're connected to a cylinder. Next, let's examine the types of directional control valves. This directional control valve can be used to control a single-acting cylinder. It has three passageways called ports. The one at the top is connected to the cylinder. At the bottom left is an exhaust port, and the port on the right is connected to a source of compressed air. The valve also has two switching positions. With 3 ports and 2 positions, it is called a 3-2 directional control valve. This design of the valve seat and seals is called a poppet valve. 3-2 directional control valves are represented by the ISO symbol on the right. This valve is shown with a push-button actuation and spring return. Unactuated, the valve blocks the flow of air to the cylinder, and air exhausts from the piston side, allowing the spring to hold the cylinder retracted. When the button is pressed, the valve shifts, connecting the compressed air port to the cylinder. This causes the cylinder to extend, and the valve blocks the exhaust port. When the push button is released, the spring built into the valve shifts it back to its starting position. The cylinder is then connected to the exhaust port, and the cylinder spring returns the cylinder to its initial position. In this industrial application of a manually actuated 3-2 directional control valve, the single-acting cylinder ejects finished parts from a clamping device when the button is pushed. Next, let's examine the 5-2 directional control valve. Like the 3-2 valve, the 5-2 valve has 2 positions, actuated and unactuated. However, this valve has 5 ports. It's represented by this ISO symbol. The 5-2 valve is used to control double-acting cylinders. Both parts at the top of the valve are connected to the cylinder. The center port on the bottom of the valve is connected to air. The 2 outside ports are exhaust ports. In its initial position, the valve directs air to the piston rod side of the cylinder, holding it in place. When the push button is pressed, the valve directs air into the piston side of the cylinder. At the same time, it exhausts air from the piston rod side. When the push button is released, the valve directs air into the piston rod side of the cylinder. At the same time, it exhausts air from the piston side. Double-acting cylinders are used in applications where work is done in both directions. For example, this clamping fixture uses compressed air to hold the plate in position. This is another type of valve, the 5-3 directional control valve. It has 3 possible positions: center, right actuated, and left actuated. Notice that there are 2 springs in the valve. These return the valve to the center position when the push button is released. The valve is represented by this ISO symbol. The 5-3 valve can be used to control the position of a rotary vane double-acting cylinder. The valve port connections are the same as the 5-2 valve. Both upper ports are connected to the cylinder. The lower ports are exhaust, air, and exhaust. In the valve's initial position, all ports are blocked. This holds the vane at its current location. Pressing the left push button sends air into the left side of the cylinder and exhausts the right side, rotating the vane. Pressing the right push button sends the air into the right side of the cylinder, rotating the vane in the opposite direction. When both push buttons are released, the springs in the valve return it to the center position and the cylinder is held in position at various rotation angles. This is a typical application of a 5-3 directional control valve. The operator can stop and hold the parts bin at any angle. There are two ways valves can be controlled. Directional control valves can be directly actuated, as shown by this roller lever actuation, or indirectly controlled by another valve, such as this push-button 3-2 valve controlling a 5-2 valve. The AND valve enables the logical AND decision to be made pneumatically. Therefore, the piston extends only when both push buttons are pressed simultaneously. AND valves are also called two-pressure valves. This shows how the two-pressure valve operates. When air enters the valve from one side, the output is blocked. If this signal is lost, and air enters the valve from the opposite side, the output is also blocked. Only when two signals enter the valve is an output signal produced. At this workstation, two parts are pressed into a housing. Two conditions must be met in order for the pressing operation to start. They are: a start signal must be present, and the machine must have completed the previous cycle. This is indicated by a limit switch located at the initial position of the cylinder. Often, machine circuits use multiple AND valves. To simplify circuit plumbing, you can use a valve block containing multiple valves. For example, this block contains 3 AND valves. Another type of logic valve is the OR valve. When one or more signals is received by this valve, it produces an output. OR valves are also called shuttle valves. As shown by this diagram, the OR valve has 2 input ports and 1 output. When a signal is received at either input port, the valve passes the signal to the output port. If 2 signals are received by the valve, the first signal produces an output and the second signal is ignored. A shuttle valve is used on this machine so that it can be started from either of 2 locations. The machine can be started by pressing a push button, or a foot pedal can be used to start the operation. The machine starts if a signal is received from either location. The 2 signals are connected together in this OR valve. Next, let's examine another type of valve, the quick exhaust valve. One way to increase actuator speed is to exhaust cylinders directly to atmosphere through the large opening in a quick exhaust valve. This avoids the longer and narrower flow passages through the directional control valves. In this example, only the first cylinder has a quick exhaust valve. When started at the same time, the first cylinder extends faster. When installed on large cylinders, the quick exhaust valve has a more noticeable effect. Using quick exhaust valves in control circuits results in higher machine cycle times and greater productivity. In applications that use large cylinders, the advantages of the quick exhaust valve are obvious. One type of pressure valve is the pressure regulator. It's responsible for holding the operating pressure constant by regulating the flow orifice. When the pressure increases, the valve automatically closes partway, reducing the flow to the circuit. The pressure regulator also smooths out pressure spikes from the machine circuit by venting excess pressure to atmosphere. Every service unit contains a pressure regulator. Next, let's examine another type of regulating valve. This is an adjustable flow control valve. Air passes through a restriction in the valve. When the size of the restriction in the valve is reduced by tightening the thumb screw, less air passes through the valve. This is a one-way flow control valve. As its name implies, the valve controls flow in only one direction. It consists of an adjustable flow control and a check valve. The flow control restricts the flow of air in one direction. In the opposite direction, the check valve opens, allowing air to bypass the flow control. One application of the one-way flow control valve is to control actuator speed in one direction and allow full speed in the opposite direction. In this machine, the piston extends slowly and then retracts at its normal speed. One type of combination valve is a sequence valve. This valve switches when a predetermined pressure is reached. In this machine, the sequence valve controls the pressure applied in pressing a shaft into a housing. The pressure valve waits until the shaft reaches the bottom of the hole. When the circuit pressure rises, it sends a signal to retract the cylinder. Another type of combination valve is the time delay. It contains a one-way flow control valve, air reservoir, and directional control valve. This valve delays the sending of a signal for a set time. The length of the time delay is controlled by adjusting the rate at which air is allowed to enter the reservoir through a flow control. Once the reservoir is filled, the directional control valve shifts, allowing the signal to continue through the circuit. In this application, the time delay valve holds the cylinder in position for a few seconds to ensure that the screw is fully seated in the hole. Earlier in this video, you learned about two types of valve actuation, direct and indirect. This is an example of direct actuation. The control valve is directly actuated by the push button. Indirect control is actually the preferred type of actuation because it allows for a separation of signal input and processing. One reason this is desirable in machine design is that it allows you to include logic functions in the circuit. To understand this better, let's examine a number of applications. In this machine, signal input is provided by the machine operator. As long as the operator presses both push buttons, the cylinder continues to extend. When the operator releases either button, the cylinder retracts. Therefore, the cylinder movement is manually controlled by the operator. This circuit contains an example of automatic signal input. When the piston reaches the end of its stroke, it actuates a limit switch. The signal generated by the limit switch shifts the 5-2 directional control valve moving the piston back to its initial position. In most applications, the roller lever actuated valve is a sensor. It generates a signal based on the position of moving parts in the machine. Here, a limit switch is used to create an automatic return circuit. Once the operator presses the push button, the sequence continues automatically until the cylinder returns to its initial position. This is the result of the interaction between piston rod, sensors, and control valves. Now that you are familiar with the individual components used in pneumatic circuits, let's examine how they form pneumatic control systems. The first component is the service unit. It's the link between the air distribution system and the pneumatic control circuit. Remember, it controls the pressure supplied to the circuit, cleans the air, and can add oil to lubricate the circuit components. The next step is to select the components that will actually perform the work. For this example, let's use a double-acting cylinder. If you connect the service unit directly to the cylinder, it will extend. However, this does not allow you to retract the cylinder. You could move the air line to the opposite port on the cylinder, retracting the cylinder. Now, when you want to extend the cylinder, you have to move the air line again. This is not a safe or practical control method. Therefore, a directional control valve is used to connect the cylinder to the service unit. This is a simple control system that provides direct actuation. In most applications, it's rare for cylinders to be directly actuated. Normally, control and signaling are accomplished using discrete components. In this circuit, two push-button directional control valves send signals to a 5-2 directional control valve. When a push button is pressed, the cylinder is actuated. Another benefit of indirect control is that even if one of the push buttons is pressed momentarily, the cylinder will complete its full operation. This is because the control element stores the signal. Another consideration is to incorporate safety features into the control system. For example, a second push-button valve was added to the extend side of this circuit. This design requires that the operator use both hands, pressing both push buttons at the same time to extend the cylinder. An AND valve is included in the circuit to provide this function. In order for the cylinder to retract, the third push button must be pressed. The structure of the pneumatic control system can be described in terms of the functions of the circuit components. The first level is the source of energy and its preparation. The second level contains components that initiate control signals. Logic functions that process these signals are located in the third level. These determine conditions that must be met before actuators are moved. The fourth level contains control elements that send air to the actuators. The fifth level contains the actuators, but not all control circuits contain separate components for each level. In simple circuits, one component may provide the functions of multiple levels. This push-button actuated directional control valve provides the functions of signaling, logic, and direct control. Next, let's look at the 5 levels using ISO symbols to represent the components. At the first level, we have the energy supply and the double-acting cylinder in the level of actuators. A 5-2 valve is used to actuate the cylinder. In this constellation, the manually operated valve acts as an input element, processing element, and final control element. We then used, in our example, two push buttons as signal elements to actuate the directional control valve. The 5-2 valve acts as processing element and final control element in this case. To enable the AND function to the circuit, a two-pressure valve is used as processing element. Let's look again at the 5 principal levels of a pneumatic circuit. Energy supply, signal elements, processing elements, control elements, actuators. Each of these levels can be identified in the actual machine circuit. The service unit is the source of energy and its preparation. The two manually operated valves initiate control signals. This AND valve provides a logic function. The 5-2 directional control valve is the control element, and the double-acting cylinder is the actuator. Regardless of their complexity, all pneumatic control systems contain these basic functional levels.